Many observers expect clear water, slightly sinuous river with pools and riffles, and some riparian trees. River health, however, is much more complicated and multifaceted. Messy rivers generally represent increased biodiversity and increased river function. Messy rivers also represent an opportunity for increased wonderment and awe for the wanderers that journey into these riparian areas. So, Ellen, I'm really excited about hearing this talk, and I appreciate you being with us today.
Well, thank you very much for the introduction. Let me just get my screen sharing enabled and we can get going. And I'll
Great.
do this as do it in presenter mode. There we go. Okay, let me just get rid of the remote that nobody else sees, but that drives me crazy because it's hiding the top of my, I don't know where, hide floating meeting controls. That's it. Okay, now we're ready, I think. Yes, so I'm going to talk about messy rivers, and that's really my shorthand for spatial heterogeneity. So spatial heterogeneity, you could think of patchiness, either in the active channel or in the river corridor as a whole. And I use river corridor to refer to the channel, the floodplain, and the underlying hyperetic zone. So patches, depending on your objective, you can have a minimum unit area that could vary from less than a square meter to multiple square meters. But the idea is that a patch is internally consistent and it differs from the adjacent areas. So again, patches reflect spatial heterogeneity. The greater the patchiness, the more heterogeneous, and messy is just a shorthand for that. Usually when I'm talking to people who are not river scientists. Sorry, I'm just trying to figure out how to, there we go, to advance. So a little bit of background before I start talking about some of the details of spatial heterogeneity. One thing I think it's really important that I'm guessing most of the people on this call are natural scientists or engineers, so physical, biological scientists. Social scientists talk about the baseline of perception or the shifting baseline of perception, and it's essentially the idea that whatever you are used to is normal. So if you grew up in an urban area and you are used to seeing a river that looks like a concrete lined canal, that's normal for you, and that's what you expect to see. And that's an extreme example, but most of us, I would say all of us, outside of the very high latitudes or some areas of the tropics, are used to seeing rivers that have a long history of human alteration. So even if that alteration is no longer occurring, it can still affect river form and process and affect what we expect to see, which in turn can affect what we consider appropriate or reasonable targets for river management or restoration. Second part of this background is just not all rivers are alike. I'm showing you a nice Google Earth image of the Yukon River in Yukon Flats in the middle of Alaska. There are lots of rivers that never look like that prior to human alteration. So it's not like we can take some particular river template and say, this is what rivers should look like. You really have to pay attention to all aspects of the environmental context, from where are you in a river network? Are you in the headwaters? Are you in a lowland floodplain river or a delta? Where are you in the world in terms of biome, climate, geologic setting? And the third one is in many ways the most difficult of all of this. What is natural? Natural is most commonly used to refer to things apart from human alteration. That may sound straightforward, but what human alteration? Are we going to say prior to indigenous peoples, if they used fire or manipulated rivers, say irrigation canals? There were extensive networks of river diversions in the southwestern US prior to the first Europeans coming in. Are we going to say prior to the Industrial Revolution, prior to extensive change in land cover? The point is what to call the starting point in time, and then how to assess what is natural. Neither of those are straightforward, but they're important considerations when talking about river process and form. So going back to the idea of baseline of perception, this is part of the inside front cover of a British textbook on river pollution. And I think everybody would look at this and say, oh, that's awful. What I found really interesting was the opposing front cover, which is this. And again, I think all of us would look at it and say, oh, that's so much better. But the more I looked at that, the more I thought, well, it's definitely a lot better, but it's not what I would call a natural river for the UK in terms of lacking human alteration. I had the chance to spend a sabbatical there, and all of the UK pretty much was historically forested, including the places we're used to thinking of as naturally grassland or moors. They're all anthropogenic. So I look at this and I say, well, there's no riparian forest. The river has sinuosity, but it's pretty uniform in many respects. So I'll come back to this pair of drawings at the end of the talk. Another aspect of sort of both perception and environmental context, most of us, when someone says river, we think of the active channel and we think of an active channel, not a system that's got a lot of connectivity between secondary channels that branch and rejoin, either anastomosing as you're seeing here or braided. Not necessarily a channel that has a lot of connectivity to floodplain wetlands, as you see in the lower right. So the paper that I'm referencing here, we were just trying to make the point that these highly connected river wetland complexes were much more common historically than they are in many parts of certainly the temperate latitudes today. And in the US, of course, this is important because we treat wetlands and channels or streams differently in terms of regulation, mitigation banking, restoration credits. There's some very important regulatory differences in how we address them or consider them, even though they're intimately connected in actual river corridors. That environmental context, again, I just want to make the point, both of these are pretty natural river corridors. This is the Alaskan tundra and the Brooks Range on the left, and then southeastern Australia and the Brisbane River on the right, but they're very, very different. So where you are in a river network and in the world makes a difference in what is, say, appropriate or desirable or achievable in terms of river management and restoration. And again, that what is natural, stepping aside for a moment from the consideration of when you want to call natural in terms of pre-human alteration, there's also the issue that natural river corridors are dynamic. You can't take a static form and say this is what the river should look like, because many rivers, apart from human intervention, change quite a lot through time. They may flip back and forth, or they may have progressive change. But understanding that natural range of variability in whatever parameter it is you want to choose. So could be flow regime, sediment dynamics, channel form. That's important, but it's difficult to do. Sometimes this is done using reference conditions where people will look for the least human altered catchment or river segment in a region. That works well in some parts of the world. It's very difficult to do in others, particularly parts of Europe and Asia, where there's a long history of human intervention. Regardless, I think it's really important to know something about land use history. The area I live in, the Colorado Front Range, many of the streams here look very natural, but if you dig into history a little bit, there's been a lot of alteration. There was massive deforestation here associated with 19th century metal mining. There was massive beaver trapping. There's a lot of flow regulation. So understanding the effects of past land uses, even if they're not occurring anymore, becomes important in trying to assess, again, what has been there in the past. That may not be what you want to restore to or manage for. It may not be feasible even if you want to, but I think it is important to know something about that land use history and know something about the characteristics of those water and sediment regimes or flow and sediment regimes apart from human alteration. So when I think about river corridors, I tend to focus on the reach scale, and I'm looking primarily at the physical context. So things like the lateral confinement. Do you have a really wide floodplain, or is it something more like a gorge? The lateral confinement often correlates with the reach scale gradient. Now, if you've got a lot of lateral confinement, you're more likely to have a steep channel that's transport dominated. And if you can see the little gray text on the right of this diagram, river ecologists sometimes refer to those as strings and the wider lower gradient portions as beads. And I've started using that terminology because it's very intuitive. Once you explain to people who are not river scientists what it is, they can immediately picture the difference between beads and strings. So I start with thinking about that physical or geomorphic context. Think about the fluxes moving through there. So water and sediment in all rivers. In historically forested catchments or river corridors, large wood was also very important. And then over on the right, thinking about the biota, and that's living animals, plants, in some cases microbial communities like biofilms can make a big difference in the critical shear stress from moving fine sediment, for example, and certainly dead wood. So the interaction of these fluxes and biota in this physical context creates what we see in a river corridor in terms of that patchiness or spatial heterogeneity, the degree of three-dimensional connectivity, the resilience or the ability to absorb disturbance and return to pre-disturbance conditions, and the physical and ecological integrity. And I would guess that most of you are familiar with that phrase, ecological integrity. Physical integrity isn't as well known, or geomorphic integrity, but it derives from a paper that Will Graff wrote at the beginning of the millennium, which sounds very, I don't know, it sounds impressive when I say it that way, but it was published in 2000. He just made the point that physical integrity reflects the ability of the river corridor to adjust to changing inputs. So if you think of a concrete lined river in an urban area, it has no physical integrity. The only thing it can do is have faster flow when there's more discharge coming in, for example. The river that I'm showing in the bead in this block diagram would have more physical integrity as the amounts of water and sediment coming in, or large wood, or the coverage of riparian vegetation change, the channel form would change. So you could think of physical integrity as ability to adjust. And again, I use that phrase river corridor to make it explicit that I'm talking about the channel of the floodplain and the underlying hypereic zone. And this block diagram looks a bit complicated, but I think it's important to make the point that things, whatever the thing is, water, mineral sediment, large wood, particulate organic matter, things don't just move simply downstream at a uniform rate. We all know this, but a lot of people who are not river scientists don't think in those terms. So there's a lot of vertical exchange with the hypereic, the shallow subsurface environment, and with the groundwater. There's exchange laterally through the banks, and in overbank, there's lateral exchange coming in from the adjacent uplands. And it's not that a natural river corridor is highly connected. There are plenty of highly disconnected natural river corridors, or there are river corridors that have strong longitudinal and limited lateral and vertical connectivity, or vice versa. So limited longitudinal, strong lateral and vertical. The point is that understanding the degree of connectivity in each of these three dimensions and the features that influence that, I think, is important to understanding how the river corridor operates. So again, conceptualizing them as river corridors, it emphasizes the interactions that occur between things like fluxes of water and sediment and the erosional resistance of the valley boundaries, the biogeochemical reactions, the living organisms, and it also emphasizes those interactions between the different components. So coming back to this idea of messiness and spatial heterogeneity, very simply, you can have heterogeneity in the active channel bed. So differences in grain size, differences in bed form type and dimension, differences in large wood. This is looking downstream to a channel spanning logjam in Hunters Creek in Rocky Mountain National Park. You can't see what's downstream of the logjam, but it's a steeper channel that's mostly a boulder bed with minimal storage of fine sediment. In this backwater from the logjam, you've got heterogeneity of the active channel in terms of fine sediment, organic material, heterogeneity of the hydraulics. There's deeper, slower flow here in the backwater, as you would expect. You can, of course, have different scales of heterogeneity in the banks. The ones I'm showing here are in a fairly small subalpine channel in southern Wyoming. You can see the little undulations. Each of those is going to have a zone of flow separation. There'll be differences in velocity, flow depth, probably a little bit of difference in substrate, hypereic exchange. Of course, at larger scales, you can have features like the root wad of a tree, whether it's living or dead, that creates a protrusion into the channel and embayments on either side, or you can have meander bends or expansions and constrictions. A variety of features can create heterogeneity in the banks. Heterogeneity of form, again, you can have asymmetry and differences in the cross-sectional area associated with things like pools and riffles, or steps and pools, or meander bends, expansions and constrictions. And then heterogeneity in plan form, the sinuosity of the channel, whether it's a single or multi-channel system, the number of secondary or partly abandoned or completely cut off channels in the floodplain. This is an aerial view of a small channel in interior Alaska, showing some really nice cut-off meanders that are now floodplain wetlands. So there's these basic dimensions that can create patchiness, but fundamentally the sources are first of all, the geology. If you're looking at the length, the entire length of a river or an entire river network, there are quite often those strings and beads. So the wider, lower gradient sections alternating with the steeper, narrower. And that's not just mountain streams. The Danube is one of the best examples I know for a big river. It alternately cuts through mountain ranges and canyons and then goes into big alluvial basins where some of the major cities like Vienna and Budapest are located. You could also have differences in lithology, glacial history, differences in jointing. All of those can create fundamental geologic processes or heterogeneities that underlie that heterogeneity of valley form. Vegetation, again, from deadwood to a variety of different types of living vegetation, say marsh vegetation in low gradient fine grain systems or woody riparian vegetation in higher energy systems. That can create a lot of heterogeneity. And then those fluxes, things coming into and moving down the river corridor, of course, vary with time and space. So all of those fundamentally interact to create spatial and temporal patterns of sediment erosion and deposition that drive things like lateral channel movement and those changes in the different dimensions I was just talking about, like bed forms and substrate or cross-sectional geometry. So one of the issues with messiness is how do you quantify it? And there are a variety of different papers that have looked at this, either just looking at topography, with this one from Scown and others from 2015 to one that Emily Iskin, who just finished her PhD at CSU, was doing, where she was using floodplain topography and vegetation as indicated in remote imagery. And each of these insets are different rivers. We were looking for the most natural rivers we could find in the US and trying to get a diversity of drainage area, flow regime, and biome. So like the one in the upper right here, Yak, is Yukon Flats in Alaska, which you've already seen. The one in the lower right is the Altamaha in Georgia. So Emily looked at a variety of these and developed a workflow for categorizing this patchiness. But again, the key is that one of the things, if you're interested in heterogeneity, is just how do you quantify it so that you can compare it between systems, and there are different metrics available. The other thing, of course, you can ask is, well, fine, so what? Why do we care about spatial heterogeneity? Well, there are a series of characteristics that are desirable in many respects that derive from that patchiness. So the first one is just habitat abundance and diversity. Going back to this site that I've already shown you different images of, there are these floodplain wetlands that are mostly filled. There are floodplain wetlands with far more open water. There's the main channel, there's secondary channels. You can see a diversity of not so much topography here as vegetation, soil moisture, or wetness levels. And as I think most of us are aware, the field of dreams, as it's been called, approach to river restoration, which is just build it and they will come, is not enough by itself. You don't necessarily get biodiversity if you have habitat abundance and diversity, but habitat abundance and diversity are an important starting point to creating biomass and biodiversity. And there are starting to be papers, if you notice this is 2022, it's just within the last 4 years that I'm starting to see papers where people are explicitly tying things like habitat abundance and diversity and biomass and biodiversity to metrics of heterogeneity and showing these correlations. So this is one example. Second implication is just what happens in a river corridor when you have a disturbance. And resistance usually means that there's very little change during the disturbance. Resilience, there may be change, but the system recovers its pre-disturbance characteristics pretty quickly. So I'll show you an example here from a beaver meadow. This is the photo montage at the top is standing on the lateral moraine looking down, and you can see the other lateral moraine in the background. The moraines are dry, well-drained sites with conifer forests. Between them is, in this photo that was taken at the end of the summer, or actually it was autumn, so the vegetation is not very green, but you can see standing water. Hopefully you can see there's channels that branch and rejoin. The bottom photo was taken at the same site in early June, just as the willows are starting to leaf out. And it's very hard to tell in this photo, but there are 3 secondary channels coming together and flowing towards me where I was standing taking the photo. This is a site with a lot of spatial heterogeneity associated with beaver modifications. As Emily and others have shown, these sites are very resistant to fire. They've got a high water table. there's a lot of surface water and there's a lot of moisture in the vegetation. For the same reasons, they're very resistant to drought. In 2013, we had the largest flood in the region of this beaver meadow. And when I was finally able to get up there after they repaired the roads and reopened the national park after a federal government shutdown, I went to the upstream end here and I couldn't tell there had been a flood until I really started poking around. If you look at that lower photo, those are really dense willow shrubs. The flow energy was very effectively dissipated moving into this part of the river corridor. Longer term impacts like climate change or resource use, again, the greater the heterogeneity, other things being equal, typically the greater the resistance or resilience to disturbance. And another example of this is from Joe Wheaton at Utah State, a fire that occurred in Idaho. It's probably 3 or 4 years ago now. The adjacent uplands were completely burned. This beaver modified portion of the river corridor, again, much wetter, didn't burn. And I think this is a pretty famous paper now. It's a great title, but Smokey the Beaver. Emily and Andrew quantified some of these effects for fires throughout the Intermountain West. Another implication, just retaining things that are moving downstream. We create irrigation canals and concrete lined rivers in urban areas because we want to limit flooding or we want to get material downstream very efficiently. Sometimes it was sewage and waste in the past. Straight, simple, homogeneous uniform maximizes conveyance. So the patchier the channel and or the river corridor are, the less efficiently things move downstream, and that can be very good. So this is a very small channel with a log jam. It's, apart from this photo, it's an extremely steep step pool channel with boulders that are 0.5 meter to 1 meter in diameter. This little log jam, which probably didn't last very long after I probably was gone the next snowmelt peak flow after I took this photo, you can see it's creating a little backwater. There's finer sediment there. There's organic material. And the people who work with macroinvertebrates and biofilms have shown that if you can slow down the movement of particulate organic matter, even for a few hours, let alone days or weeks, you can greatly increase the biological availability and uptake of that material. And of course, if you've got more spatial heterogeneity in the form of obstructions like in-stream wood or beaver dams or islands or bars, that's going to probably increase the connectivity with the floodplain. So you may be dispersing and storing material there. So biological availability, dispersal, dilution can all strongly correlate with the degree of heterogeneity. And again, some examples of this, the upper one, we were looking at large wood being trapped in river corridors, and the lower one, we were looking at finer, coarse particulate organic material. That sounded contradictory. I meant finer than large wood. But this organic matter, we were working in southern Utah and Arizona. You get accumulations of that, and they're hotspots for a lot of things. That the soil moisture tends to be greater under there. As that material decays, it releases nutrients to the soil. They're habitat patches for invertebrates and then for the creatures that eat them, from lizards and snakes to songbirds. So it makes a difference whether you retain this material or just pass it downstream. Another implication is connectivity. And here again, it's not that heterogeneity necessarily increases or decreases connectivity. It depends on the details. The photo you're looking at here, which is from the west side of Rocky Mountain National Park, there's a relict beaver lodge in the lower right there. There would have been beaver dams across here in the past, and when those were present, they would have reduced longitudinal connectivity, or upstream, downstream, but they would have increased vertical connectivity with the hyporeic zone and lateral connectivity with the floodplain. So again, the details of the patchiness or spatial heterogeneity and what's creating it strongly influence connectivity. And again, fairly recent, all this, the older one is from 20 years ago now, looking at some of the effects of connectivity, both the causes of connectivity or disconnectivity, and then the effects of that on, in the case of the upper paper, biomass and biodiversity. Okay, so back in 1969, my predecessor at Colorado State University, Stan Shum, used the phrase river metamorphosis to describe what had happened to rivers in eastern Colorado that had gone from being braided with minimal woody riparian vegetation to much narrower, deeper, more consistent hydrographs with dense floodplain vegetation, and that was the product of flow regulation primarily in Colorado. But of course, the phrase river metamorphosis could be used to refer to any progressive change over differing timescales. So I'm using it here to refer to this change that we see throughout higher income societies or industrialized societies, from more spatially heterogeneous to more homogeneous, simplified river corridors. A lot of that, again, is driven by the presence or absence of the spatial and temporal variations in those fluxes, so water, sediment, large wood, as well as living biota, both animals, plants, and microbial communities in some cases, and by the presence or absence of that physical integrity and the ability to adjust to the variations in those inputs and biota. And one of the things that I've seen in the rivers of the Colorado Front Range that I think applies to a lot of rivers, certainly throughout the US, is that they've become leaky as they've become more homogeneous and uniform. Wherever you may be in the US, if you go back and look at some of the first written descriptions, I've read this in historic descriptions from the Southeast, the Northeast, the Great Plains, the Pacific Northwest, the Rockies, the Southwestern US. The first descriptions, people complain a lot, whether they're going up or downstream. They have to get out of their boats and portage a lot. They can't figure out where the channel is in some cases. So we have to think of many of our rivers as being much more highly connected river wetland corridors with a lot of standing water, either backwaters from naturally occurring wood rafts or secondary channels that branch and took someone off down a detour and made it hard to get back to the main channel, beaver dams on the smaller rivers, et cetera. And as we, as a society, have removed those obstructions and channelized the rivers and stabilized the banks to create flood control or improve navigation, the rivers essentially pass things downstream much more efficiently now. So we've lost that heterogeneity and retention. And two examples of very large rivers from Europe. The upper left is a painting of the Rhine. You can see it was more like an anastomosing system, and the picture on the right always makes me think of an interstate, two big navigation channels. And then the Danube near Linz, Austria, if you can see the numbers in the upper right here, 1812 and 1991. This particular part of the Danube in 1991 doesn't have as much urban development, and so the floodplain is still there, but that complexity of secondary channels branching and rejoining has largely been lost, and that was primarily for navigation and flood control. And I could have included images for the Mississippi, the Ohio, the Illinois, take your pick, the Missouri, many of our large rivers as well. All right, so again, what? People talk about river health, and the phrase is a little bit controversial because it's hard to define, or individual people using the phrase may be meaning different things. But it's a phrase that I think persists because it's intuitive. Now, if you talk about human health, you can be sick, you can be healthy, you can be terminally ill, et cetera. So it's a concept that's kind of easy for people who are not river scientists to think about when they think about rivers. So I'm going to just say healthy here means functional and providing some of the ecosystem services that we commonly desire. So evidence that spatial heterogeneity creates and maintains those. This was Nick Sutphin's PhD work. He was looking at organic carbon storage in downed wood and mostly in floodplain soils. And if you look at the two summary statements here, those beads, or the unconfined valley segments, they're a small proportion of the total river length, less than a quarter. But we quantified carbon storage in different types of river corridors and in the uplands, and then extrapolated that to the whole river network. And those beads are disproportionately important. And that's on a per unit area, not just because the beads are wider than the strings, but because if you have a hydrologically connected floodplain, you're probably going to have high primary productivity. So lots of plant litter dropping into the soil. The soil is more likely to be saturated and have reducing conditions. So you end up with higher concentrations of organic carbon in the soil, and that soil is also likely to be thicker in the floodplain than it is in those string segments. And what really surprised me was that the valleys are less than 1% of the total area in the river catchment, but they store almost a quarter of the carbon because, again, the organic carbon concentrations in soil are so much higher than they are in the upland soils. And this work was done in Rocky Mountain National Park. And then Deanna Laurel, this was her PhD work. She looked at beaver meadows, same type of thing. They're disproportionately important. While the beaver are present and you have dams and saturated floodplains, you store a lot of carbon in there. Even if the beaver disappear for some reason, the dams fall into disrepair, the channel, the flow concentrates into a single channel that incisors and reduces the floodplain water table. You still store a lot of carbon there in those relic soils. Second line of evidence, again, getting back to retention or leakiness, keeping material in the channel for a while, creating hypereic exchange that promotes nitrate removal and greater biomass. So Bridget Livers, this was her dissertation research. She was part of a big multidisciplinary group. We were working in Rocky Mountain National Park. The one thing I found that surprised me, I knew that the old growth forests had more large wood in the channels and floodplain, and they were going to have more spatial heterogeneity. What surprised me, though, was we had a population of 3 different types of river corridors. They were old growth forest, which means older than 200 years for the average stand age. Younger but naturally disturbed forests, so less than 200 years for average tree age, but no history of timber harvest or other alteration. And then younger disturbed forest or managed forest. These were forests that had a history of timber harvest or wood removal, although nothing had been done in them for a century. And what surprised me was that the old growth and the naturally disturbed forest were statistically similar, but they were both different than the historically managed forest. So even a century after management, there was still this persistent legacy in terms of the large wood in the channels, which then equates to differences in pools and riffles, particularly pool volumes. It can equate to the presence of multi-channel systems where secondary channels branch and rejoin downstream, and a lot of retention in the pools and secondary channels of things like particulate organic matter. Our colleagues on this project found that there was greater hypereic exchange and nitrate uptake in those systems with more large wood and spatial heterogeneity. And we didn't find more macroinvertebrates, but we found more of their predators. So there were more fish and riparian spiders, salmonids and riparian spiders that were eating the fish. Excuse me, eating the macroinvertebrates.
Mm-hmm.
Third line of evidence, this one hopefully is common sense. If you have a variety of different flow paths in the surface and subsurface, you've got a broader distribution of hydrologic residence times. This is from work on a gravel bed river in northwestern Montana. And the greater distribution of hydrologic residence times then can be equated to things like nutrient uptake and just attenuating peak flows if you've got some of the water moving downstream more slowly in the subsurface. And working at the same site, they showed that there's this mosaic of things like riverine denitrification or nitrate uptake and soil carbon storage, again, because you've got this patchy river corridor with a variety of different environments. So just to put this in historical context, a lot of my work has been done in the Intermountain West, but globally, of course, we've almost completely removed old growth forest, and there's a long history of removing wood from river corridors. So we've reduced forest cover by half globally and almost eliminated old growth. And ecologists sometimes talk about alternative states. So it's 2 very different configurations of a particular system. In this case, it would be a river corridor, each of which can be stable and persistent, but you need some type of disturbance to move from one to the other. So my highly technical terms for this in terms of wood are wood rich and wood poor. And the wood rich, these are both examples from Rocky Mountain National Park. The one on the left, the wood rich, is old growth. There's no history of timber harvest here. The amount of wood that comes into the channel varies a lot from year to year. We have insect infestations, we have blowdowns, we have periodic fires. But as long as there's some wood in the channel, it's very effective at trapping other wood. And this picture of this, what's quite a large logjam for that channel, there are some very stable pieces, and they're trapping a lot of the more mobile pieces that are coming downstream. The photo on the right is from a lower elevation in the park where there was a history of timber harvest, almost complete deforestation before the park was designated in 1915. And even though the forest has grown back, it's a simpler system. So you see the tree that's about to fall in this photo, there's a lot less to trap it when it does fall in. So a variety of studies that use space for time substitution and numerical modeling have shown that it takes about 200 years after you deforest an area and remove all the in-stream wood before you go back to pre-human disturbance levels of wood loading. Same type of thing for beavers. The estimates are something like 6 to 12 million in North America in this enormous range because it's poorly constrained historically, but a lot more beaver, somewhere between 60 and 400 million. And this is one of the most famous examples of alternative states for river corridors. Ecologists refer to these as beaver meadows and elk grasslands. So on the left, the beaver meadow, beaver build dams, they build a lot of dams and they move around a lot. So you'll have a river corridor where there's a variety of patches on the floodplain, recently built dams and newly flooded areas, abandoned dams that may have channels, or excuse me, backwaters that are gradually filling or completely filled and supporting wet meadows. But it's a very spatially heterogeneous environment. The alternative here, and both of these are in Rocky Mountain National Park, has been called elk grasslands. And I'm guessing many of you are familiar with the story in Yellowstone National Park, where a lot of the rivers look like many of the rivers in Rocky Mountain National Park today. Very unnaturally high density of wild ungulates, mostly elk and moose in Rocky Mountain. They outcompete the beavers and they eat the willows to the point where they're gone or they're just rootstock. So you end up with a scenario where the beavers can't survive. They disappear from an area, their dams fall into disrepair. Peak flows are more likely to be concentrated in a single main channel and to both erode the banks and incise that channel. That lowers the local riparian water table and the whole section of river corridor becomes drier. So now, if you were to drop off a happily mated couple of Mr. and Mrs. Beaver, it would be really hard for them to survive here. It would be hard to build a dam that would withstand peak flows, and they need the woody riparian vegetation for winter food, and there's not a lot here. So in the case of Rocky Mountain, the Park Service has built quite a few grazing exclosures to keep the elk and moose out, and they're building beaver dam analogs. And in at least one case, the beaver have moved in and built a better dam on top of the beaver dam analog, and they seem to be doing very well. Beyond those examples, of course, there's these ubiquitous alterations that we as humans have implemented. Global flow regulation. Diversions are very, very difficult to map. There's no good records of them, but just looking at large dams, less than a quarter of the rivers in the world still flow uninterrupted to the ocean. There's widespread channelization. There's artificial levees, and Rich Knox was one of my PhD students who did the first cut at mapping artificial levees throughout the US. You would think, or I would have thought before we started that work, that there would be very complete databases on these things for the US, but there weren't. So he had to develop a remote sensing workflow to detect them and then map them. And in parts of the country, of course, that's a major influence on river connectivity between the channel and floodplain. So how messy should it be? Well, it depends on where you are, again, in the river network and in the world. So environmental context and land use history, these are just three kind of randomly chosen photos making the point that quite apart from what we as humans do, natural rivers are quite diverse. So it varies depending on where you are. And I think we can think about this in some of these controls. This is a diagram I use a lot from David Knighton's textbook on fluvial forms and processes from the last millennium, where he's got increasing length scale on the y-axis from essentially instantaneous changes to geologic timescales at the top, and then moving from left to right on the x-axis, the very local, like dunes and ripples in a sandbed channel, to catchment scale processes. So at the largest time and space scales, we're not doing much as humans. We are changing climate, but climate and tectonics are sort of independent variables for a lot of what we do. It's at the short to intermediate timescales and small to intermediate space scales that our activities within the catchment, things like changing land cover, and within the river corridor in the form of river engineering, have the most effect. And the net effect of that has been to reduce the spatial heterogeneity of most river corridors. So as we go forward, a lot of river engineering and management now is focused on trying to restore some of these characteristics that I've been talking about, like spatial heterogeneity, physical integrity, ecological integrity. I think as river scientists and practitioners, an important consideration is that you can do things on an ad hoc basis, which is what we mostly do. Somebody wants a river restoration project here. Okay, let's see what we can do. But we also need to start thinking about the catchment scale context. And back in 2011, Margaret Palmer and Emily Bernhardt had a nice paper titled The Fuzzy Logic of River Restoration. And the point they made was that if you have catchment scale degradation, and they were looking at this in the context of nitrate loads, how many reach scale restoration projects do you need to mitigate or even reverse that? We can't answer that question right now. We've made tremendous progress as a river science community in the last couple of decades in coupling hydraulics and sediment transport, particularly for sand-sized materials. We now have two-dimensional models for large wood, for riparian vegetation. I think what we need to start doing is integrating across different types of models so that we can have as an outcome predicting things like spatial heterogeneity and these three-dimensional fluxes, and then tying that to whatever it is that's desired in the context of management, like organic carbon stock or nitrate uptake or biomass. And that really presents an opportunity for, I think, scientists and practitioners to collaborate. So I want to leave you with this idea that when you look at a river, you will think of these three-dimensional fluxes and the patchiness or heterogeneity and some of the effects of that. Think about that occurring in the context of a river corridor and think about the processes that create and maintain that. So if I come back to that parrot image that I started with, I asked one of our grad students who's a good artist to rethink the boy and the dog. And I'm not sure what happened to the dog, but the boy is catching a fish now. And there's a little more heterogeneity in this. So there's, first of all, there's wood or woody vegetation in the riparian zone. There's a little bit of age diversity. There's downwood. There's a little bit more variation in the varial zone, or that seasonally inundated and exposed section. There's a secondary channel going across the meander. There's some diversity in the water surface indicating bed forms and differences in grain size distribution. So it's a little bit more like what I'd expect to see in a place like the UK. And the citations that have just come up here are all papers that look at this idea that when many people think about river restoration, they start with a single channel in sort of an open park-like woodland with moderate sinuosity, which is fine. There are settings where that is exactly what you would have expected prior to human alteration, but there are a lot of settings where that's not the case. So if we can broaden our perceptions of what's feasible or what's desirable, I think that would be really useful. And if you're interested in knowing more about the history of changes in the continental US, over the last few years, I've had a graduate seminar where we've put together a series of case studies. These are story maps of different rivers that hope we're one of the things we're trying to achieve is just get people thinking more about the fact that pretty much anywhere you go in the contiguous US, you can assume there's a history of modification that affected the river corridor, even if that modification is no longer occurring. And of course, an example of trying to reverse some of that, even on a limited scale, this is a project from the Dolomites in Italy. And on the left, the 2005 image, you can see a series of check dams, and there's a lot of bank stabilization. And you can see the floodplain has land uses and communities. This river would be naturally braided, and when people proposed to restore it to this, there was a lot of resistance from the local community. They did not perceive a braided river as being aesthetically pleasing or desirable or even natural in that setting. The project was able to go forward, and I was there in 2018 in November. It was not a very pleasant day. It was probably in the 40s. It was drizzling. There were so many people out on that river corridor. They were walking their dogs, they were fishing, they were watching birds, they were jogging. There was a lot of public use. The project has now won an EU Water Framework Directive prize, and the local community is very proud of it. And they're trying to convince the communities up and downstream to do something similar. So if you're looking at this photo on the right, you can see there's still check dams. The river isn't reoccupying the entire river corridor that it would have had historically. So I want to show this because I think it's important to make the point that river management and restoration are not an all or nothing, natural or, well, this is hopeless. As I think you all know, it occurs along a continuum. And even in the most constrained urban areas, there's often something you can do to create a little more heterogeneity and patchiness and river function. And just a nice example of, in this case, using place names in different languages to look at the past occurrence of these more spatially heterogeneous systems across several European countries. So I will stop there, and I'm happy to take questions if we have time.
Yeah, we do. We have about 11 minutes or so, but thank you so much. This is a wonderful presentation. Does anybody have any questions just right off the top before we I do have a couple questions myself. All right, I'll get us started. The Marriott River that you present on at the very end kind of brings up one of my questions, but introducing that messiness, that heterogeneity in urban environments, it seems to be one of the more challenging practices or in stream restoration, because in urban environments you're dealing with a lot of site constraints, you're dealing with utilities, you're dealing with landowners, you're dealing with structures, that sort of thing. And that messiness can lead to uncertainty, or can appear as an uncertainty. So I guess, are there some really low-hanging fruit kind of tools that we can put in our tool belt for introducing more heterogeneity in those urban environments?
Yeah, and I think so. I'm on sabbatical leave this year, so I've been able to travel a little bit more than normal. And in September, I was at a river management conference in Japan where Matt Condolf spoke. He's at the University of California at Berkeley, and he had some really spectacular examples of urban river restoration. I was delighted to see that I wasn't aware of. The Isar River in Munich, for example, was the one I remember off the top of my head. But I think the key is that in many larger cities, they're recognizing that with climate change, you may have an increase in peak flows as rainfall becomes more intense. So the Dutch really started this with their Room for the Rivers program. I think everybody, if you can see me in your inset,
Mm-hmm.
I'll just describe it. Let's say my hands are 3 feet apart. That was the historic floodplain. Now my hands are 3 inches apart. That's the contemporary floodplain. The idea behind Room for Rivers is that maybe you go out to 6 inches or a foot.
Mm-hmm.
So you're not reoccupying the whole floodplain, but you're giving a little more space. And in the Netherlands, they're doing that because it's literally a matter of life and death. They're below sea level, and sea level is rising, and it's getting wetter there. So they have got to increase the conveyance on their rivers, and they're doing that by increasing the width of the floodplain that can be accessed. And in the example of the Isar, as I recall, what they did, they're very constrained by the urban infrastructure, but wherever they could, they created essentially artificial beads. So they created places, and I remember Matt had a photo of people in summer sunbathing on a gravel bed in the middle of a very urban setting. So I'll use the city I live in, Fort Collins. It's about 150,000 people. We have some natural areas along the river. Those are the beads. Those are the places where you can focus river restoration. In between, yeah, it's too constrained. So I think looking at where there are opportunities, either to acquire land, and that's often after a flood disaster because people have trouble getting reinsured or they want to sell out. And even where it's more constrained, um, thinking about what's sort of been called river miniaturization. So not just creating a wide, um, frankly, very boring concrete canal, but having a small inset river in there, that a place where maybe you remove or modify some of the bed stabilization and allow some riparian vegetation to come back. I know I saw Ellie Papangelakis was on this call a few years ago. I had the chance to go to some of the sites in Toronto, and I was so impressed. Their parks are little natural areas. So it's an urban river in between those, and there's still constraints like culverts and underground pipes. But within those beads, they created a pretty functional and pretty heterogeneous environment. So that was a long version of figure out where you've got degrees of freedom and work within those. And maybe you're not going to restore all the sources of heterogeneity,
Right.
but maybe you can do a few.
That's great. Josh, I saw your hand go up first. Go ahead.
Yeah, hi, Ellen. This is Josh Gilman. I'm a longtime fan of your work. Love your message. I was first exposed to you when when I was working with Colorado River with the Grand Canyon Monitoring and Research Center, and in the last 30 years, we as practitioners we've seen the needle shift in a little bit in the right direction, and your message and exhortation of practitioners and trying to elevate, good stewardship, knowledge and practice. Sometimes it feels like we're moving in that direction much more slowly than we are with our disruptive behaviors. And currently, I think a lot of us have found that that legislation is not very effective at changing some of these paradigms. What do you think is going to be maybe an episodic event or a shift in paradigm, or are we going to continue down this gradual path and hope that we intersect and interrupt where we're headed? What are your thoughts there, Ellen?
Okay, looking into my non-existent crystal ball, I think episodic can be really important, and I'm going to cite an example that literally just occurred last week in Colorado. The state came up with a beaver management plan, and we have never had one. And implicit in that plan is the recognition that if we can restore beaver populations where possible, that's going to create a lot of desirable effects in terms of both carbon storage and water storage and attenuation of very flashy peak flows in sized degraded systems. People who are practitioners in Colorado, many of them have recognized that for at least a decade, but the governor bought into it. It was a big deal. They not only initiated this statewide beaver management plan, but he made basically a public address emphasizing the importance of beaver. So that's an example. I mean, I guess what I'd say, Josh, is episodic can go the other way too. I mean, a lot depends on our Supreme Court. The couple of the decisions like Rapanos and the others have taken us back a long way in time. So on a state-by-state basis or a national basis, a lot depends on the political climate. I think, is it, let's think globally, act locally. We have to do that for river restoration too. We have to keep working for progressive incremental change and hope that there are going to be episodic realizations that move us forward a lot. I once heard a social activist talk, and somebody asked, I don't even remember what she worked on. This was many years ago. Someone said, how do you maintain your optimism? And all she did was say, what's the alternative?
Oh, yeah. I like it. Thank you.
That's great. Yeah, thank you. Chuck, I see your hand raised. And then we'll get to you next, Ahmed.
So you had brought up the issue of connectivity and some barriers that the guy you were referencing, he had to use some sort of GIS analysis to get the locations of those. We guess sometime last year became aware of something called the Southeast Aquatic Resource Partnership. Basically, it's aquatic connectivity. I don't know if y'all have heard of that or not, but
yeah,
they started the Louisiana aquatic connectivity team. And so just wanted to point that out.
Yeah, thank you for mentioning that. In some places where there's been a longer history of artificial levee construction, there's more known about the distribution of these. And the Corps of Engineers has a database, but it's not complete. But I think all the regional efforts that, what Rich Knox did for his PhD was an important start, but there's a lot more to be done yet. And I think having regional databases like the one for the Southeast is critical.
Yeah, I think that American Rivers has made an objective of theirs to create an aquatic connectivities team in almost every state. I think they're pretty close. So if you guys are interested, it's I belong to the North Carolina Aquatic Connectivity Team, and it's a great organization to be a part of. All right.
I know in December of last year they conducted some training for people going out and classifying, categorizing these barriers. Could be culverts or what have you.
Absolutely.
So that's another big unknown culvert distribution.
I think we have time for one more question. Ahmed, go ahead.
Yeah, thank you. Yeah, I'm Firdaus Ahmed. I work for Water's Edge in Ontario, Canada. I work with Ed Gazendam. Anyway, so I have a question. So, all the things you are describing, Professor Wohl, is intuitively right, and we can all appreciate this is the first step in any scientific endeavor to understand qualitatively what is happening, which you have presented very well. And I think there is enough evidence that, yes, something is going on here with rivers and we should be doing something differently. The question in my mind is that all these nice pictures and all the description, everything is fine. But at the next step, we need some kind of quantification of the different variables, their relationship, and the mathematics behind it, and things like that. That's necessary for the understanding of the physical process, but it is also necessary to resolve dispute between the people, because people might have different opinion about how the river should look. So how do we settle those things? So my question is, from the qualitative side, we kind of understand what is the current situation on the quantitative side, the mathematical side of it, or how do you foresee it is unfolding in the future?
Yeah, it's a very good question. I think the slide that I had talking about integrative modeling is how I hope I see it unfolding in the future, but I'll give you some examples from the work that I'm involved in. We know it's very apparent that channel floodplain connectivity results in peak flow attenuation, and there are models of that.
Yeah.
But what I find interesting is that those models are simplified in some very important ways. For example, they often treat the floodplain as an impervious surface, even though we know that in dry regions in particular, groundwater recharge is key in overbank floods. So I'd say the first thing is we need all, George Bach said, all models are wrong, but some are useful. So
Yes, that's
you
right.
have to simplify the complex natural world, but I think we need to think carefully about some of the existing simplifications. Another example, nitrate uptake. We know that obstructions, whether it's bed forms or beaver dams or log jams, increase hyporheic exchange, and there are both field-based studies, there are physical experiments, and there are numerical models of this, but we have not tied that to nitrate uptake, for example, or to cumulative effects. So we know what one log does. My group has measured what one log jam does, but what if you have 10 in sequence? And that's proving to be extraordinarily difficult to measure in the field. So we're working with hydrologists who use three-dimensional numerical models to try and scale up. So I think I completely agree with your point that we absolutely need quantitative measurements, both to talk about the magnitude of the processes and to try and understand what the response might be to our manipulations. And I think those have to be integrated or begin to include more variables. It's exactly the same thing with climate change models. They can be infinitely complex, and they keep getting better as we add more of this complexity. So we've got to do that for rivers. Just one last example, people have looked at individual effects of beaver dams. So they've looked at the hyporheic exchange, or they've looked at the effect on base flow or peak flow. But I have yet to see a study that is an integrated water balance that includes transpiration, evaporation, subsurface storage, stream flow effects. Those are hard to do and they're expensive, but that's the type of integration I think we need going forward.
Yeah, those are pretty extremely difficult things to do, even without beaver and nitrate uptaking all these things. All these are added layers of complexity. But anyway, thank you very much. I appreciate your talk, and I've been following your work for many years now. I'm not in the river science itself, but in the peripheral hydraulic modeling and hydraulic engineering.
We're happy to have you. Thank you, Vertus. Dave, see your hand raised. You want to close this out?
Oh, sure. Hey, Ellen, we really appreciate everything that you've done for us. We're very thankful for you giving us this time. One challenge that I'd like to talk to you in the future about is how is river restoration able to affect people from a mental health aspect in the future? I see a huge opportunity I think I read in an Oprah magazine on a plane this weekend that everybody looks for something bigger than themselves. And that seems pretty fluffy. But I think that when it comes to river restoration and messy rivers, there's something really big about knowing that there's been so much more complicated than what we can understand.
I couldn't agree more, Dave. I'll just say briefly that this talk was written for mostly or prepared for non-scientists. And when I give it to general audiences, I get a really enthusiastic response. And think about what happens when people advertise a river cleanup. How many people show up to pull out old tires and old shopping carts? Yeah, I think I completely agree that this could be a very emotional connection for people.
I'm gonna move to a religious thought just because it's a word that's been used, but there's a word in religious language called ecclesia, and all it means is gathering of people. And historically, we gather of people in different places around natural things that we found value in, like rivers. And we've kind of forgotten the value of rivers, and we don't show up at rivers too often. So, man, seeing messier rivers, having people be more amazed by rivers seems to be a huge potential for what we can give back to our society as this community of river restoration scientists.
Agree.
All right. Well, Ellen, thank you again. This is wonderful. Thank you, everybody, for sitting in on the conversation, and have a great week.
Thanks for the good questions, everyone.
All right.
Thank you very much.
Bye.
Thanks, Ellen.
Hey, thank you, Ellen, for being able to coordinate that today. I've been on the vehicle for the whole call with the earbuds in. So it was a great talk, but I really appreciate you being able to be on the line and coordinate that, and look forward to having you be able to be involved in more of these. We have some other really great speakers coming up soon. So hopefully it's something you can find really fun and exciting.
Absolutely. Thank you so much, Dave. And travel safe. And when the recording's ready, I can upload it to our shared platform.
Yeah, I'll forward it to you. I don't know if the emails go to you or not, but I know they go to me. So once they go to me, I'll just forward it on to you. So.
Okay, that sounds good. And then I am right now, we're still being recorded. Before I upload to our shared platform, do you want me to try and edit or cut the recording down at all, so that there isn't this kind of like before everyone chimes in and afterwards?
I think that would be great. It's an easy clip inside of Zoom before you export it.
Okay.
But talk to Molly and Paula about it, because Paula has been cutting them for us, because sometimes we'll have two different types of talks. We'll have a technical talk and then an inspirational discussion, or an inspirational talk and then a technical discussion. But when the talks go a little bit longer, we just kind of do it as one day type of thing. So just work with Molly and Paula and see what works out best for them. I can't claim to think that I've known how to do it right, but we've kind of gone along. That's about it. So.
Okay, that sounds good. And then just to make sure, do I just hit the stop button when we're done?
Yeah.
And it'll.
Yeah.
Okay.
Once you hit done, you just hit end, and we'll end the meeting for everybody. Or if you have a co-host who will say, "Do you want to transfer it to the co-host?"